Hello, ladies and gentlemen, and welcome to Compliance for All's live webinar on ATC Radar Approach Control. My name is Michael, and I'll be your host for today's session. And on behalf of the Compliance for All team, I'd like to thank you all for being part of today's session. Today's webinar is being presented by Mr. Stephen Albania. Before we start off today's session, a few words about our speaker, Stephen. He's had over 30 years of experience with the U.S. Federal Aviation Administration, and he's also a certified air traffic controller at an airport traffic control tower and a radar approach control and an en route ATC center. And he's also led the development and deployment of the National Traffic Flow Management System. And he's also worked as a technical research program manager for multiple advanced ATC capabilities, and also he's a FAA HQ ATC procedure specialist. And his expertise includes aviation committee staff for the U.S. House of Representatives Committee on Science, Space, and Technology, ATC subject matter expert for ASAP Census Corporation, and also currently Stephen is the owner of Air Traffic Consulting Systems LLC. And we are honored to have Stephen with us today to present today's webinar. Ladies and gentlemen, before we start off today's session, I'd like to quickly inform you of the program outline. This webinar is for a 90-minute duration. First, Stephen will take you through today's webinar, highlighting the areas he would cover and then share with you his presentation. And also, we would like to inform all our participants today that once part of today's teleconference, you're being placed on mute and would remain so until the Q&A begins. We have a couple of minutes at the end for your question and answers, but if you do come up with questions during the session, please post your questions in the Q&A panel or the chat messenger. And for any reason, ladies and gentlemen, if you do get logged out of today's session, please follow the same procedure to join in again. Now that we're all ready, I request Stephen to take it from you. Stephen?
Thank you, Michael. Am I coming in okay?
Absolutely, Stephen.
Okay, great. Okay, thank you very much, and welcome everybody to the webinar. Michael's done a good job of going through this, so I'll just skip this section and get on to the objective. And the objective here is this, and we've all heard the expressions about there are things that you know, things you know you don't know, things you don't know you know, and things you don't know that you don't know, which is the one that is the most problematic. So that's why I want to focus on teaching people or exposing people to things that they really don't know about the ATC system. The question is, well, why do I want to do that? Okay, well, the first thing is I'm assuming that everybody who here has a professional interest in understanding the ATC system, and to a level that is fairly significant and at least can that has a sense of appreciation for what the system really is, beyond your curiosity or an interest in it. And oops, why did that? That's what's supposed to do that. There we go. And one of the things that, the reason why I'm doing this is that the system's like an iceberg. People see it out there and say, oh, it's beautiful and it works well and all this type of thing. But most of the complexity and most of the messiness, and also most of the beauty of the system lies beneath the waterline and is not obvious to an observer. You can ask questions, you can do this, you can do that, but there's still many parts of the system that most people don't know about how it works. And I experienced that when I was the subject matter expert. People would be asking me questions, we'll be talking about something, and something would come up, and I'd be curious, well, why aren't they asking me about this? So I would offer the information, and I began to realize they didn't know to ask the question. So the thought to asking the question never occurred to them. So that's when I began to get on a mission here to kind of help people understand those things that they don't know. And the reason why it's important is that an incomplete understanding of the operational problems, and that's what I'm focusing on too, is not so much the technology or the mechanics or the logistics, but the operational problems. And if you don't understand those well, if you don't have a full appreciation for the messiness of the system and its elegance, that can lead to flawed technical solutions that you offer the agency or in the development of new technologies. They're flawed because they've simplified the problem and really haven't addressed the hard stuff, the messy stuff that makes things so much more complicated. But if you don't do that, or if you do that, then what you produce is something that is limited and insufficient utility to the users. They're saying, well, okay, that's fine what you're doing, but I need to do more. I need you to help me with the hard part. And once they begin to get the sense that you have left out the hard part, then they lose confidence in you as a developer. And at that point, that's kind of like strike three, and at that point, it's very difficult to regain the confidence of the customer. Okay, so I want to kind of help people understand that complexity so they can be more credible, have a better understanding and more appreciation for what the controllers or the users of the system are actually facing. And today's, we're going to discuss, the terminal radar approach control, the TRACON operations. A few weeks ago, we had one, the initial webinar on some of the basic concepts of ATC that underlie all this. So we've kind of covered a lot of that, and I'll start from there and work on now focusing in on a particular facility type. So people who didn't attend that, it shouldn't be a real loss, but may make it a little bit more difficult now to kind of follow what I'm saying. Not really difficult, but just a little more difficult. Anyway, so let's get on with that. And before we do, though, I just wanted to, this time I put this in all my briefings just to make sure I don't get sued by somebody. This is not, an official proposal or concept or direction to anybody. The views I present here are my own based upon all these years of experience and observation and just interaction with all these people. But I don't represent anybody. I don't represent the government, the business associations, or unions, or anybody else, okay? The next thing I want to say is what I'm going to be going through here is not to show you how they run traffic at Chicago or Los Angeles or a particular airport. Every airport is completely unique. It's very much, they're all the same, but yet they're all very, very unique. So if you need that kind of information, it's best to go there, talk to people who work there, and get that level of detail and currency. What I'm going through here is a sense to kind of show you what the context is, what they're facing, that applies to all facilities, not just a particular facility someplace. And the last thing is, I use a lot of videos and a lot of games here to try to get the idea across. And I use them because I find them to be the most useful for what I need, as far as getting people to understand. And it shouldn't be construed as a kind of an official endorsement of them. There's sort of many, many of these out there. These are the ones that I've come across that I find most useful. So I use them for my own personal preferences. I have talked to them, get their approval, but I'm not being paid or anything else by anybody else. So don't take these as endorsements, just suggestions or thoughts on my part. Okay, let's get started. Okay, to rehash a little bit, like I said last time, there's these 5 facility types in the ATC system. The flight service stations, the towers, TRACON centers, and the command center. The first one are the flight service stations, which used to be at all these airports. That's where pilots got all their services and filed their flight plans, got their weather, type of thing. That's now done basically online. And it also still is the center of the facility efforts to do search and rescue if that's ever required. But it's now done online primarily, and it is not a control facility. It's an information service. It's many, many services. In fact, it does more for pilots than ATC does, but it does not control the airplanes. So basically, we can just kind of eliminate that one as being part of the 4, which leaves these 4. Okay, and first one is the tower, which we all have seen before, the big tall structure there, and that provides a rolling flow of traffic between the runways and the parking areas, back and forth. Departures going out, arrivals coming in. Okay, the next one down would be the TRACON, which we're talking about today. This one is right here at the base of the tower in this particular configuration. Many airports, with technology nowadays, it doesn't really matter where they are. They used to be right there beneath the tower cab because of technology, but then as you could do with more data, they move them down here, then off the airport, and now they could be almost anywhere. But what these facilities do are provide the separation and sequencing services at or about or near the major airport, or airport or airports. So it's the close-in, detailed separation and sequencing of traffic near major areas. The next one down is the centers, of which there are 20, and this is basically the mothership of air traffic control. This does everything And what really happens is the TRACON and the tower have taken things away from because they need more precision, have been pulled out of the center operation so they can be done more efficiently. But they provide all ATC services outside of the TRACON and tower airspace and perform everything else. And then the last one is the command center. And this one is a single facility, and it monitors the demand throughout the entire United States of the demand for air traffic services. It monitors the demand, it monitors the capacities of airports and sectors and intersections and a lot of things to look for and project into the future, into the significant future, areas of imbalance between demand and capacity, and looking for projections of major delays and disruptions. And once it discovers those, it creates large-scale strategies to try to mollify or to go around or to deal with that situation. So those are the facilities in the system. Okay, and now we're focusing today on, well, this is the ATC and this is flow management. That's how they break out. Okay, this is separating airplanes. This is managing traffic flows. Next thing down, this is in those facilities. They are all allocated specific airspace. Okay, so in this case, here you have two airports that are out there in the beginning, and all they are is strips of concrete or whatever, even grass or land. But they're out there, and as traffic builds, someone says, well, this is going to be too busy. We need to put in some kind of a safety thing here to create some order. So at that point, you put in a tower cabin, okay, which is there to provide that order around the airport, the local airport area. Okay, and in that, as soon as you put one in, by statute, there is airspace assigned to that. And it's below 2,000 feet above the ground and a 5-mile radius of the airport. Okay, that's called the airport traffic area, and that's what the tower kind of owns that airspace. And airplanes passing through that airspace are supposed to contact the tower to get assistance, to be advised of traffic in the area and to be told who to follow and that type of thing. So they serve as a positive service for aircraft. So that's the airport's traffic area in the tower. And then, as if you need more to control that, then they add on a TRACON that envelops the airport traffic area. And the TRACON now is the one that provides that traffic separation sequencing near the airport. And its airspace allocation is usually 50 miles, which was the range of the radar, of the airport surveillance radar, about 50 miles. Okay, and the airspace above it was usually, back in the day, was like 7,000 feet, but since the strike in it, now it goes up to whatever it needs, and some are as high as 23. So these are all variable, and one thing about the FAA or the AT, Air Traffic Control System, that I really admire is its flexibility to adapt to what it needs to be done and what it has to work with. So in this case, the 50 miles is kind of the limit because of the radar range, unless you consolidate TRACONs into a single building, and then you have multiple radars. And the altitude is what is necessary. So as you go on then, if you need that, there's another tower over here, another airport, you may or may not want to put in the tower. Okay, so that could be or could not be there. It could or could not be part of the TRACON. The TRACON can be expanded to include that one also. Okay, so that's the way this TRACON and the tower airspace works. And then once the next level of airspace is the center. This is the en route facility. It owns everything else. Okay, up to by level 600, which is the top of serviceable and controlled airspace. There are 20 of these throughout the United States. This is the way they're configured, and there is no missing space. It covers all the airspace. And then not above, but socially, but basically just the next level is the command center, which now provides that strategic planning for all the traffic that occurs within all these control facilities, which are these. This is a control facility. A tower, TRACON, and the center are all control facilities. The command center is the strategic planning facility. So that's the structure of the airspace in the system. And like I said, it doesn't control airplanes. Okay, so now getting into the TRACONs. Okay, you can look at this. What's unique about it is the positions in the TRACON are single-person positions. That means there's one person there who's responsible for the airplanes that under his jurisdiction. Okay, and this is the way they've usually configured, like this, one person in a scope. And this is a basic TRACON looks like this, and then it'll be checked 2 more over here. Okay, and this is where the flight strips print out, or whatever you're going to have here is printed out. So you have departure controller, 2 departure controllers over here who work together, and here's 2 arrival controllers over here. And the reason why they have to work together is because the 2 of these guys are agreeing among themselves the order of the airplanes that will be on final. So, assuming you have a single final approach course to a runway, these 2 people coordinate with each other to say, okay, I'm going to follow your American airline with my United or whatever. They talk to each other back and forth to work out the sequence, then they make that sequence work. Okay, there's a bay in there, they put the strips in order, and then they make that work. So it's critical these 2 people kind of sit side by side and be able to talk to each other. Okay, this is the basic configuration. Now, this is your basic one. Now, if the facility is bigger, you can add other things. But this is the departure control and the arrival control. Okay, and like I said, the departure controllers over here take the airplane once it lifts off. Tyler sends them to departure control. He takes them from the airport departure runway out to the departure fix, separating the airplane from other departures and from arrivals that are coming in. The arrival controller does something similar, takes them from the center, from the en route facility, brings them down and sequences them to the final approach course. Those are the 2 things right there. I'd say there's additional functions that are now that the centers have gone up to higher airspace, that they actually perform. There's satellite airports, which means it's not the primary airport, but they provide approach control services to smaller airports that are out there that have one approach and very few airplanes. But they provide that services to those kind of airports contained within the TRACON airspace. And now also there's a lot of tower en route, which means the airplane it goes through their airspace. He's not landing, he's just passing through. So it's a tower en route airplane that goes through, and there's positions, or 1 or more positions that can handle that. Now, what you can do is, again, the beauty of the flexibility is you can have 1 person doing all these. This person here may be a mid-shift, maybe a Sunday morning. This person here may be handling all these particular functions, or it can be opened up as needed to be. Anyway, but this is the basic configuration of a TRACON. This is how it looks from a different angle. Okay, now, like I say, they can get very, very large. And this one is a picture of, and it looks to me like it's a pre-operational picture of the Potomac TRACON, which is the one that was recently consolidated here in Washington. It combines the TRACONs that did exist at Baltimore, Washington National, Dulles, Richmond, and Andrews. And so I'll put them into one facility. So this is the way you can see the positions all along the back along there, and I'm sure there's a lot of positions along there. So this is how big they can be. In addition to those 4 we saw on the previous page, you can have very large facilities made up of a lot of positions within the TRACON. And this is how TRACON's surveillance display looks. Okay, looks very cluttered. This takes a long time to learn what all these little marks mean, because all these marks mean something to the controllers. You can see here, this is the final approach course. Here's the runways right there to an airport. Here's one final approach course coming in this way, and another one coming in this way. They're converging runways. Okay. And you can see there's an airplane there, an airplane there, an airplane there. Probably one up here. He's going to turn it into the localizer there and bring them in. So you can see this is one controller feeding this runway down here. But every other mark on here is significant information to the controllers. These are probably airspace boundaries along here as far as who owns what, where, and you'll see in a minute here what I'm talking about there. But this is the airspace allocations within the TRACON. But this is what a TRACON display looks like. Okay, now getting down to the very basics, right, from the very basic idea of what a TRACON does. Okay, what it does first of all is let's say for your departures. Okay, this is one left and one right. Okay, so if your departures are taking off north like this, if the guy's going to the east, there's an east departure fix. Going to the west, there's a west departure fix. They lift off, tower transfers them to the approach controller or departure controller. He takes them this way and takes them to the east of the appropriate departure fix. Okay, and in this case, the procedure would be he climbs to 6. Just internally agreed to position and procedures. Same time, the approach controllers out there are taking aircraft from the arrival fixes, and they're coming in this way, and they'll bring them out here, turn them on the downwind leg, and they will, according to procedures, descend to 7,000 feet. So you have these guys going to 7, these guys climbing to 6. Okay. The next step is once they go down this way and they actually pass, the departure controller will climb the departures to whatever he's going to his departure fixed altitude. Climb departures. The approach controller will descend the arrivals. Okay. And it's important. This is important to point out. The procedures are there to minimize coordination. They are agreed to procedures, and the reason why is, say, if you have a west departure, an east departure, and an east arrival and a west arrival, you have 4 people working this traffic. So if there are no procedures, everybody has to talk to everybody else. Say, for example, this guy's taking off and he's going this way. You may see that the arrival guy has a guy coming up here, and he'll say, north of the airport, can I climb east? And he'll say, yes, that's approved. Go up that way. So you have to work with each other to make sure the airplanes don't go into conflict. If things get really, really busy, you're spending all of your time talking to each other and not handling many airplanes. So by putting in procedures, what you do is just institutionalize what you're going to be doing. It's all agreed to. So therefore, if it's really busy, this person, the departure controller, can climb to the airplane here, climb to 6, head out this way, and then go here, climb to whatever he's going to, hand him off. The arrival controller comes in here, descends to 7, comes in here, descends to 3 or whatever, and they pass. Never talk to each other, and that's the point of the procedures. Of course, now, if it's not all that busy and you're doing that, you just coordinate to say, okay, you're north of the airport, we're going east, can I climb? And this person will say it's approved. Okay, so the procedures are there to minimize coordination when you need them, but if traffic is late, you're fully expected, and they all do talk to each other to get the airplanes either up or down as fast as they can, or as fast as they need. Anyway, so that's the initial phase of it. And then after that, you're now merging arrivals from other fixes, arrival fixes, coming in this way too. And now you're creating kind of a common downwind leg on both sides of the airport. Okay. At this point, the 2 approach controllers sitting side by side talk to each other and figure out, okay, what are the names of the airplanes that are and their order for this final approach course. They agree to that, then they make that work. Okay, so this is the final approach course agreed to back here. And they just turn the airplanes in, and there's a lot of coordination and a lot of working, hopefully, well together. Okay. And this is the basic, the core functionality of the way a TRACON works. Okay. Okay, now in real life now, it gets a little more complicated, starting off here. This is Cleveland TRACON, and here's the arrival fixes. Arrival fix here, these are the holding patterns where in the event they have to hold, this is the established the established holding patterns for the 4 arrival fixes. Okay, so here are the arrivals coming in here, landing here in Cleveland. Up here, they merge this way. But this is how the streams are merged by the approach controllers. There's probably 2, this guy and this guy, maybe this guy and this guy. But they come in here and they merge right there to create the final approach course. Okay, put the traffic on the final approach course. So that's the arrivals. So now at the same time, you have departures taking off, and they're going down there, going up there, going up that way, and you can see how all those paths cross. And to try to coordinate a lot of arrivals with a lot of departures would be a hideous process in just talking to other controllers. So by putting in procedures, you can do this much, much more easily, move much, much more traffic. But you can see this is where this area, the TRACON area, this is the alpha and the omega of ATC. This is where they start and where they stop. And this is the merging and the meshing of all that traffic. Now, a little more details now. Boy, this is Pittsburgh TRACON. And this is an old picture, but the principle is the same. This is the picture of the display, okay? And the area in gray here is the airspace that is owned by a departure controller. And it is the departure south position in a west flow. It's not departure southwest flow. It's departure south, which means there's another departure up here, which is departure north. And the west flow means traffic is taking off and landing to the west. So it's a west flow, departure north, departure south. And this gray area are the airspace chunks, the airspace corridors that this departure controller owns. If I'm the departure controller, this is my home space that I can do whatever I want in this airspace. So if I go out in somebody else's airspace, I have to coordinate. So, but this is my airspace. And you can see here, right here, I own from surface to 5. Okay. I come down here, I'm surface to 14. Here, surface to 3. Here, I'm 9 to 14. And the idea, you can see there's quarters. So an example would be, well, and also too, I want to point out, before I forget, this bird does on 14 and below. Okay, and down here we have Allegheny County Airport and a Washington, Pennsylvania County Airport. Okay, you notice in here now, this is the airspace that I own as a departure controller. And I own the surface to 2.5, surface to 3, surface to 5, surface to 5. And over here too, I also own 8 to 14 and 8 to 14. So therefore, I own airspace that is beneath and above the final approach course for aircraft landing to the airport. The approach controller owns in between there. But that's how this airspace is divided to create quarters and little holes I can go through to get airplanes in and out. This airspace configuration is very complicated, but it has evolved over years and years and years of traffic evolution and trying to squeeze out every single bit of airspace usage that you can. An example of this, okay, if I get departure, I'll turn. He's going southbound. I'll turn to the left out here. I own surface to 5, so I'll climb to 5. When I cross this boundary right here, I own surface to 14. I'll now climb to 14, and then I'll hand them off to Cleveland Center, somewhere along here when I'm getting near the top of my airspace. So I turn them south, stay in my airspace, cross the boundary, go to 14, and hand them off to Cleveland Center. At the same time, I own the Washington County Airport here. Here on surface to 4, and this guy wants to go up that direction. Okay, so I'll climb to 4. When I get into here, this airspace, I can now climb to 14 again as I go up there. And once I get out of 8,000 feet, I can cut across and go straight up that way. Okay, I just crossed there at 8,000 feet. Same time, out of Allegheny County Airport, I may have an airplane wants to take off and wants to go this direction. Okay. So here I'll climb up, I'll go surface to 5, again, climb to 14, and head them up in that direction. And now I own them all here, and the controller's job is to make sure these airplanes stay separated in that airspace. So that's what his job is, and it looks something like this. Okay. So that's the job of the departure controller. Okay, and you can see there's a lot of stuff in here. Okay, here on the surface to 5, and then 9 to 14. So this airspace can be very complicated to just understand and see, but it all is very, very specific with very, very specific uses to it. But that's the way the departure controller works. Okay. Now, if you can go to, now we have a video I wanted to show people how this works. If we can go to the video, I guess it's the Atlanta departures video. I think that's the way Michael said to do that. You can probably draw yours up, and I think I'm going to also share mine. Okay, man. Okay, no, I don't want that. Oops, I got to go back to that. Now this is Atlanta Airport, and it just shows how these departures and the arrivals have to merge with each other. Hopefully that's clear enough. It looks clear here. I'm not sure. Hopefully you're getting it down there. But here's departures in the morning rush, the arrivals coming in, and these departures are going off in different directions, and just how those streams have to cross. And this is what the departure and the arrival controllers are trying to make happen. Okay, the arrivals are entering downwind leg and taking off. You can see how complicated this traffic can be in the TRACON airspace with all the crossing traffic. The crossing traffic is where as you would expect, the most difficult part of this whole thing. Okay, so now I can stop sharing. How do I? Okay, stop sharing. Okay, I'll go back to this. Okay. And this is the last thing, getting a little small guy out here. You can just stay out here, go at 5,000 feet to leave the area. So enough of that. Okay, now for the arrivals, this is what the arrival controller does. And the primary tool of the arrival controller is the instrument approach system, okay? Instrument landing system, the ILS. It's been around for a long, long time. And it's made up of 4 parts. One is the approach lights, okay? That's these things along here. It's part of the landing system. And there's something in it called a rabbit, too. It's got a nickname, but it's the sequence flashers. So in times of low visibility, they're just the lights. You may see it at the airports if you live near one, where there's just the flasher light that goes down there, which helps the pilots identify the landing runway and the approach in use. So it helps them just guide them to the airport. So that's the approach lights. Then there's the glide slope. The glide slope is a beam that goes out from the end of the runway up at a certain angle that shows you the glide slope that you should be on to land right near the threshold of the runway. Okay, right there. Accompanying that is a thing called the localizer, which now is the narrow beam that goes down the center of the runway, goes straight up, and that tells you where you are relative to the center line of the runway. Okay, and then the markers, the outer, the middle, and the inner, and that tells you how far you are away from the runway threshold. Here in the cockpit, there's only one of these, but it shows a before and after what you're trying to accomplish. This is the ILS indicator in the cockpit, and this line here tells you where you are relative to the glide slope. So here's your airplane. This tells you are beneath the glide slope. And here's your localizer, which means you are to the left of the center line. So as a pilot, you would maneuver the airplane and trying to get to where you are on the glide slope and on the localizer, and you follow that beam into the runway. And as you pass over the outer marker, the middle marker, and inner marker, you know how far you are from the end of the runway. So it gives you a sense of awareness and a sense of where you are relative to the runway. So that's the tools that they use. Okay, I'm going to go through 2 different type of approaches, the ILS and the visual approach, and those are the 2 extremes as far as sophistication and complexity go. The ILS being the most, of course. So what you do now with the ILS procedures, using this equipment, the radar controller just sits there talking to the airplanes, and he's using his tools, which is radar vectors, altitude assignments, and speed control, to get the airplane down here where it can join that ILS system beneath the glide slope, because what you want the airplane to do is to fly level and then run into the glide slope and then start down. You don't want the airplane to be chasing the glide slope. That's not a situation you want an airplane to be in that close to the ground. So you just turn them out here, leave them have them level, runs in the glide slope, and starts down. So below the glide slope, no less than 1 mile from the outer marker. So it's got to be at least out here, because you want to have a certain amount of distance where the airplane is in stable flight. Okay, in too close, there's not enough time. You want to have them out here where things don't get too squirrely too fast. And it should be, when you turn them on, it should be less than 15-degree turn to turn on the final approach course. So that's how you do this. You bring the airplane down there, and it looks something like this. It comes in there, turns the leg, turns them on, and goes that way. Okay. Now this is the way it works. And this is an example. This is an example of why I'm talking about why things you don't know possibly. Back when I first went up into the R&D part of FAA, there was a system then that was trying to replace and upgrade the ILS system. It's called microwave landing. And the technology was phenomenal. Okay, it was really, really good and that type of thing, and it allowed for curved approaches, from all over the place, without being dependent upon this single beam, the localizer and the glide slope. So it had all kinds of huge advances in technology and capabilities that never went anywhere. And the reason for that is because it didn't factor in that they made the simplifying assumption didn't consider all these other airplanes. And the fact that they are of different capabilities, different speeds, different characteristics. And this is where the problem is. In addition to traffic coming in from other arrival fixes, and they have to be merged. And that, while that MLS helped one airplane do this, it did nothing for all the other airplanes that had to do it too. And you're trying for minimum separation at the threshold. Okay, so the hard part was not addressed. So then you try to do that, give it to the field, and they say, well, we don't want that. how are we going to deal with curved approaches when we can't see how they fit nice and neatly relative to a straight line? Anyway, so that's one of the reasons why he just kind of floundered for a while and basically has disappeared as far as I know. But that's one of those things where something failed because we didn't, the developers did not include the hard part of the technology. So anyway, so that's the ILS. The other end is called a visual approach, which is where an airplane lands visually. It's not VFR, like we discussed last time. He's still under the supervision and protection of the ATC system, which makes it a visual approach as opposed to proceeding VFR. So there is no vertical or navigation guidance whatsoever. The weather conditions must be better than VFR. Okay, so to make sure that he doesn't get in trouble. And all that has to happen is the pilot is coming in. One thing is, as a controller, pilot gets near the airport, who knows how far away, it's a nice day, maybe 15, 20, 30 miles away. And you say, do you see the airport? And he says, you're landing on one right. He said, do you see the airport? He says, yes, I do. So, okay, roger, clear visual approach, one right. You can even say, do you see, well, first one would be the runway. The second one would be the airport. And another one is if you see the traffic in front of you, 747, a British Airways 747 in front of you. Yes, I see him. Follow him. Clear visual approach. So that's all you really have to have is required. So it's a very efficient way to do that, and a very simple way to do that in those kind of conditions. Interestingly enough, it's not used in heavy traffic. Places like Chicago O'Hare with a lot of traffic, a visual approach, we clear for the visual approach, it then goes to the pilot, and the pilot can then say, well, I feel like, well, I want to turn in now. It's in the cockpit's determination when I want to turn in, turn base leg, or what I want to do. Places like Chicago, you don't want that kind of flexibility or that kind of uncertainty in the system. When the controller at Chicago says, I want you to turn now, he wants you to turn now. Okay, so therefore they rarely ever use visual approaches except if traffic is very, very light. But if traffic is heavy or very busy, a visual approach is too uncertain to be used, too often there. Okay, so that's the visual approach. Now this is now for the arrival controller. Now this is his airspace. This is arrival south in the west globe. This is the airspace that fits in between the departure controller's airspace. If you match up the two airspace configurations, you'll see these fit like a glove. Okay. So what happens here now? Here's the outer marker for the two runways at Pittsburgh, 28 left, 28 right. Okay, so there's the final approach course right along there, the ILS. Okay, and you'll see here, this is holding pattern airspace, 6 to 14. That means if there is a holding pattern, then they can be at 14,000 feet at the top. Those airplanes can all be handed over to the TRACON. The TRACON then would lower them down and pull them out when it gets below 10 into his own airspace. But anyway, so this is the holding pattern airspace. And this is where the controller brings them in and begins to vector them for final approach course. He's going to bring them in this way, descend them to on a 4, the surface, turn them on a downwind leg, and then the arrival controller owns it from between 3 and 7, 4 and 7, and 6 and 7. So bring them in here and turn them on the final approach course. Okay. Okay. Now, because I deal it, well, let me see. Let's do this first. Okay. And you'll see. And the other graphic, the departure controller owns 2.5 to 6, and well, whatever, you'll see. Anyway, here what I'm trying to point out is the arrival controller owns the airspace in between the airspace that the departure controller owns. So this is what you're trying to accomplish here. This is arrival from a departure south position, and one from the departure north, the arrival north position, and the airplanes should be brought in that way, staying within their airspace, join the localizer. They've agreed to that sequence, join the localizer, and proceed inbound. And that's the way the two work together to achieve this particular effect. Okay, now if you go to the Atlanta arrivals now, the video for the Atlanta arrivals, let's see if we can bring that up. I don't think that works. Let me try that. This shows you how they run approaches at Atlanta. Okay. Now here you have Atlanta's airports. There's the two sets of parallels, and then the outboard runway over here, and they're landing to the west. Okay. And there's the first arrivals. They come on a downwind leg, and they turn them on this way. The primaries are the two outboard runways over here. Your standard. The inboards are your departures, and the outboards are the arrivals. So that's where you come in here. There's the one coming in here, and one over there, and be two different controllers. As people see all those airplanes out there, they think, my God, one person is handling all the traffic. And in reality, the airspace and procedure is such that it's really not. Now coming up this way. And this is the extended center line of the two runways. And he's turning along to the left runway, here for the approach. And you see this, he's turning this guy in close here. So why is he doing that? You'll see here in a second. Okay. So they've opened up the third parallel. So now you have one controller handling this runway, the person on here handling this runway, and up here is handling this runway. So you have three controllers working that final approach course to Atlanta. And you can see the way that works is the person coming in this way goes to 4,000 feet. This guy goes to 5. This guy goes to 6. So when they turned on, they all have a 1,000-foot separation to them. So they all separated. And then they join the localizer and descend, and everybody is working just fine then. But this is how it's worked at a place like Chicago, Atlanta. Okay. Okay. Now, so that's we're going through the airspace structure as it is internal to a TRACON, and between the controllers, the arrivals, departure controllers, and all the other controllers. So they have that airspace structure, and that airspace structure we discussed here, like for Pittsburgh or any place else. In the TRACON, the airspace structure is a function of the configuration of the runway configuration that's in use. So when we showed you there's a departure south for the west flow, when Pittsburgh flips around and operates to the east, then there's a departure southeast flow. So all the airspace changes. So for each configuration an airport has, there is a whole set of airspace assignments and quarters that people have to be aware of and stay within. So in addition to internal airspace for the TRACON, they also have adjacent facilities that they have to worry about, adjacent approach controls. This is Syracuse right here, off to the right, and Syracuse owns at or below 10,000 feet. Okay. Here's Rome approach control, okay, and that also owns at or below 10,000 feet. Here's Rochester at or below 10,000 feet. Let's see what else appears. Just gone blanking what this is. I forgot. Anyway, but another push control up here, and it owns 6 and below. Okay, and below 6,000 feet. Above 6,000 feet is owned by Boston Center. Okay, down here is Boston Center again, at or above the surface. And down here is Elmira, that owns at or below 8,000 feet, and New York Center owns above 8,000 feet, like 9 and above. So all these airspace boundaries and jurisdictions now surround Syracuse, for example. So as a controller, airplane going through your airspace at 10,000 feet, he goes through Rome airspace. Rome hands it off to Syracuse, takes it through Syracuse airspace, and it gets down here. The controller hands it off to, down here he's at 10,000 feet, hands it off to New York Center, as opposed to Elmira, because he's at 10,000 feet. So you have to be aware of all that airspace, too, to make sure that your plane goes to the right controller and the airplane's hands off to the right controller. So there's a lot of stuff to remember in the TRACON. And now, in addition to adjacent approach controls, there's now the center above the TRACON. So here, now Syracuse is kind of unique. In fact, it has 3 centers that kind of join right at Syracuse. So right here you have this sector up, okay. This is Boston Center up here, Boston Center, and this is Watertown Low, and this is Hancock Low. Okay. So it's Boston Center. Over here is Cleveland Center, and the Rochester Low sector. And down here is New York Center with the Binghamton Low sector. Anyway, so that's kind of unique. But the Air Force, the big part of being a controller is knowing the airspace you own or who is adjacent to yours. And you can see there's internal airspace within the TRACON. There's adjacent TRACONs that abut your facility, and there's airspace above you which belongs to the centers. So just knowing the airspace is a big part of the job, and itself can be very, very confusing. So in addition to all that, now remember back in the when we talked about the VFR traffic and how as traffic builds and builds and builds, and the VFRs become more and more risky to have them flying around out, not being controlled by ATC, they put in more restrictions. And this is a thing called Class B airspace, which is near around Pittsburgh. And Class B airspace means that to be going, if you want to enter Class B airspace, that you have to be talking to ATC, okay? And you have to follow directions and maintain altitudes and basically operate as if you were an IFR qualified pilot. If you don't want to talk to ATC, another thing about the ATC system is they try to design airspace to minimally impede all the users. So if you're a VFR operator and you don't want to talk to ATC, but you're going up here, for example, you can take off from Washington County Airport up here, and you can see the airspace. The airspace here is 48. That's what the IFR airplanes are operating in. So if you stay below that, stay below these altitudes, you can go right along here, underneath, right near the airport, and just stay out of the way, and you can go fairly directly to wherever you're going just by staying beneath. You can go almost over the city of Pittsburgh and not be in the way. So this is a VFR chart. This doesn't apply too much to controllers because they don't really care too much about this, except when you violate the airspace. And then they care, and that's when they will actually write you up if you're a VFR pilot. You penetrated the airspace without authorization. So that's the airspace structures there. Yeah. And you see the shelving there. They come in, from the west, landing Pittsburgh. Here on 4 to 8,000 feet was the IFRs. They descend down to here, and 2.5 to 8 to land. So, and the airspace, like I say here, if you fly here at below 4,000 feet, you're fine. Anyway, so that's the way it works. That's more airspace structures within the TRACON airspace. Now, we talked about up to this point one TRACON. Okay, that has all this stuff to deal with and how that works. Okay, now it gets a little more complicated as major airports grow and are relatively close to each other. And getting back to Cleveland, here, this is Cleveland departures. Okay, and this is what we showed earlier with Cleveland as an example, and that's their departure routes as they hand them off from the TRACON to the centers to go en route to get out of the area. So that's a Cleveland departure patterns, flows, and then their arrivals come in this way. And all these little shelves are all airspace shelves owned by this either the centers or the TRACONs. Okay, so that's the Cleveland we discussed earlier. So now right near it, what happened up here? Is Detroit up here. Now here's the Detroit departures. Okay, and you can see that the Detroit departures cross, or interact with the Cleveland arrivals and the departures. Now here's the Detroit arrivals. They're coming in. And there are procedures set up within the centers to separate all those airplanes as best you can to keep them separated procedurally. And then finally now it's Pittsburgh. Here's Pittsburgh departures. And then in Pittsburgh arrivals. Okay, and you can see just the way the procedures are set up. Airplanes landing in Detroit are tucked beneath other traffic into Cleveland or into Pittsburgh, and vice versa. You can just see that if you look closely at these paths and routings, how they have intertwined the two to make that work as well as it can. And this is something to think about too. This situation like here, many people say, well, how can we automate this? How can we make this more efficient? And you can see the difficulty trying to do that. This is not a simple problem. And people unfortunately kind of focus on, well, let's do the arrivals or something and disregard what the impact is on the departures. So, but it's a very complicated thing, and this is stuff is usually kind of, so this is the messy part, and oftentimes is overlooked or tried to find some way to get around. Anyway, so as you can see now, this is New York TRACON and their south flow. And you can just see how the same thing applies to New York. These airports are even closer together than they are between Detroit and Cleveland and Pittsburgh. So that's the Cleveland, or the New York plan. And this is one that's always kind of neat. This is the old San Francisco, the Bay TRACON, before it became part of the NorCal consolidated TRACON. But this is easier to see. And one thing I want to show you is you can, so here's San Francisco. And you can see the departures come on, and San Francisco is the primary airport. It has most of the traffic. Okay, so it gets first cut at the airspace. So the departures go up here, and they have kind of a nice clean shot. And even their arrivals come in, go to 11, then go to 4, and so the airspace is kind of designed to support and to accommodate San Francisco because they have most of the traffic in here. And you can see where the arrivals here are beneath the departures, which is you would expect at that point, and same thing. Now up here at Oakland, and now Oakland has much less traffic, so therefore it has to keep its traffic beneath the San Francisco departures, and work out this way. And stay beneath their arrivals like you would expect. And here it could get down early, to get beneath the Frisco arrivals. Okay. But the one that's interesting is the San Jose down here. And even traffic going to the north is to take off, go to the right, to get up above their own arrivals and the Moffett arrivals, go up this way and go up this way. That's where their traffic flow has to go to accommodate the traffic. So you can see how this stuff is just so tightly integrated to try to capture the use of all the airspace you possibly can in some feasible way. So that's the Bay TRACON in the Northwest plan. Now, at the same time, there is a Southeast plan, which does the same thing with entirely different traffic flows. And you can see how complicated this can try to be and try to find some way. And like I said, this stuff here, these procedures have evolved over years and years of evolving traffic by people who work this stuff every single day. And then there's always an effort to come in to say, well, we'll bring in some kind of a group, some kind of analysis group to figure out a way to do it better. And I can't imagine that being possible with people who don't work this stuff every single day. So it's a complicated, very complicated, and elegant. This is a very elegant solution to a lot of traffic demand. Okay, so what helps the controllers a lot in that kind of situation is establishing SIDs and stars. Now, SID is a standard instrument departure, and a star is a standard terminal arrival route. Okay, and this is kind of one of these simulations that I've used. This is not a simulation here. This is just a screenshot. But one of the websites that I use is called BigFatSimulations.com, and they've got a lot of kind of games and stuff there that are very interesting, and some I think were very valuable as far as just providing education to people. And the way this works, what a Sidney star is. Well, first, before I even do that, let me do that. What you have here are the stars. Okay, these are the standard terminal arrival routes. So you can see coming in here, there's music. One at 6. I can't read the numbers. 6 and 11. They come in over this way. It's come out here and turn automatically, and these guys come in and turn automatically this way. And what this does is reduce the. These all do the same thing. Okay, you can see how the routes are. Okay, and what this really does is it doesn't really help the traffic. What this really does is simply reduce the amount of communications required for every airplane. So if he's assigned to this particular star, he has a plate that tells him what all these turns are, and he does it. Otherwise, the controller has to tell him to do it or give him radar vectors for all this stuff, which really increases the workload. So this is a communication, a workload reducer in the form of reducing the communications burdens on the controllers. Anyway, and the ones down here are the SIDS. That take off out of this Orange Island airport. They go straight up this way and up this way. This is a diverging course and a straight course. And this is the same type of thing. So it just shows you kind of a starting point where the pilots will be flying automatically to reduce the verbiage. So that's the stars, and those are the SIDS. Okay. And also on this map here are these minimum vectoring altitudes. In these blocks are places where you can't descend below the altitude because of obstruction of some sort or for some reason. It could be noise. Anyway, and this is the pending of traffic list. Now what the controller tries to do with this is to work his traffic. So he has departures off of Orange Island, and they can go to all those different departure fixes. Okay, there's one for the smaller airplanes. This is like the jets. Smaller airplanes take the Village 3 departure, and they come down this way and can go to those departure fixes. And this is not a SID. This is just the turn them to get them out of the way of a departing jet, for example. Off this airport, he goes down this way, or he can go out that way. Okay, so that's the departures. Now here's the arrivals. This the airport over there. Okay. Anyway, so that's the this is the traffic flows. And you can see that there are still a lot of congestion. These come in and help a little bit, but the big problem is still getting all this traffic to and from where it wants to go, and that's what the controller's job is in the TRACON airspace. And it's very rare you have an airport that has a nice steady stream of traffic going to the same airport, similar type of aircrafts, and this could be like the Atlantis, and the DFWs, the airports that are like that. But there aren't very many of those. Most airports are as messy as this, if not worse so. Okay. So now, the bottom line of what I wanted to try to get across to everybody today is internalizing the process. It's one thing to kind of see it and talk about it and that type of thing, but it's another thing to get a sense of what it feels like to be a controller. Okay, and that's what, if you walk away with nothing else, I'd like you to have that. And the one sense that really is, I want you to experience is the controller's nightmare. The controller's nightmare is the idea of losing the flick, it's called, which means going down the pooper. What happens is a phenomenon that occurs where you're working traffic and it's getting busier and busier, and all of a sudden something happens you didn't expect, and that is all of a sudden you have gone your own capacity to process information, and your mind goes blank. And it goes absolutely blank, and there is nothing more frightening than that, because you've got a lot of those airplanes all flying around out there, and you can't pause the problem. You can't put everybody in hold. You can't. The problem's going on, and you have to refigure it out and catch up as soon as you possibly can. So, if you can go to the other video that says RCHE, which is Radar Chaos Hawaii Edition, and let me show you that. And this is if you play with this one, this gives you a good sense of of what it feels like to be a controller. Yeah. And down like that. Okay, this is the Rare Chaos Hawaii edition. There are a lot of simulations out there. There are some that are very simple, you know, and one is called ATCSim.com, which is a fun thing to play, and it gives you some experience of vectoring airplanes and that. And it does achieve this level of getting swamped too. But there are very simple ones. There are some that are very, very complicated. One is called TRACON 2012, I think it is, which is so incredibly realistic. And it gets bogged down in the technology. It gets bogged down in you know, the voice recognition system and the details of displays and that it gets to be really, it's not fun. Where this has it's a nice mix of being fun and easy, yet complicated enough to kind of get your attention. So what this combination of this little simulation does, it's a combination of the suite of sectors. There's these 1, 2, 3, 4 TRACONs and a high altitude simulation of the en route airspace. And I'll bring this one up when we discuss the centers. A nice one that kind of captures it the best, I think, is this is Hawaii. This is Oahu. And what you have here, starting now, this is the parallel runways for departures and arrivals. And they take off the right one way, and these lines here are the tracks that the airplanes fly. And this first guy's taken off, and this one, this is Alaska Airlines. Oh, again, I need sound on it. Okay. Okay, and he's going to go to Molokai. That's where his flight plan calls for. But if I give him direct now, I'll climb him to 16. Okay. But if he goes direct, okay, I give him 16. But if I clear him direct, he'll go directly over Honolulu and Waikiki. So the procedure would be is to go down here, come out over the water, and then take him out there. Okay. So I'll turn him in some time. But the departure fixes off of Honolulu are to go down here over Molokai, to go down this way, and then to go back out this way, over these 3 departure fixes, and then back up this way. And that's the departure fixes. You also have arrivals that come in this way. And you can have a lot of arrivals except the handoff here. Here's a PA-31 in Navajo. Another guy here coming in this way. The arrivals come.
969 with you, 7,000.
Okay, so this one comes in, and I'll descend him to 3,000 feet. He's coming in this way, and I'll clear him for the approach now because he is on a star. He's going to come in here. I've cleared him to 3,000 feet, and for the approach, I'll come in here and then turn final and land. This guy here is landing on the other runway, so I want to get him down here. Now to send him to 2.
969, maintain 2,000, right heading 150.
I'll turn this guy direct to Molokai now. And this person here, I'll give him a heading about 280 and go to 4. Because I also have large and small airplanes coming in this way. The Navajos I'll take down to 2, but the Dash 8s I'll take down to 3, and the Jets I'll take down to 4. Speed it up a little bit. At this point I'll hand off to the controller, next controller. Here's another one. Took the handoff. I'll switch him.
With you, 17,000. 683, maintain 4,000, left heading 280.
Okay, so we're set there. I want to turn. I'm taking this guy because these people, this airplane here is landing on this crossing runway. So I'll take him down here. I want to turn him on down here. So now I'll just turn him back a little bit. So he's got a vector toward it.
9, 6, 9, left heading 1, 2, 0.
Let's speed it up a little bit. Okay. Qantas, he's going down over Choco. So I can just climb him right now and just go right direct. Now you could have arrivals coming in here with a departure they have to cross. So that's a control problem right there. And then you're merging traffic coming in this way, and these people here, these two airplanes here, are going over here to follow the Japan Airlines, and he's coming in there. Step that handoff. This is the Havilland, so I'll just, or Dash 8. So I always take them about heading. I have my own procedures that I set up when I go to 3 with the Havillands. Oh, I know. I forgot to turn the traffic level up to 10, which just makes it a little more interesting than this. Yeah, so. Anyway, so I think this may be, well, let me just show you how this works. So I've got these two airplanes here and this airplane over here, and they all have to line up on this runway here. This is how you would vector these airplanes.
9, 6,
So here,
left heading
go to 3,
0, 0.
looking for the approach. The question now is, can I get both these airplanes in front of this American or not? I think I can. I want to turn them on about a mile or so from this thing right there, which is I consider to be the outer marker. I'll turn right to 050, go to 3, and clearing for the approach.
Right heading 0, 5, 0. Clear for the approach.
Yeah, this, like I said, this is light traffic. I forgot to turn the traffic volume up to 10, where it makes it more interesting than this. This is a pretty light traffic load. If I get uneasy about this, I may have to pull him, reduce his airspeed a bit, make sure there's enough room between this plane and this plane. Don't think I'm going to have to, though. But I'm a little bit short.
9, 6, 8, 3, right heading 2, 9, 0.
Yeah, I think I'm going to pull this guy back about 200 knots. Turn him on.
969, left heading 070, cleared for the approach.
I think I'll turn him on now.
Hawaiian 683, maintain 3000, right heading 050, cleared for the approach.
There you go. It may even work out. Can't see him okay. He's doing 270. He's doing 220, so he's faster speed. He's clear for the approach. Everything is fine. Now you have the 3 airplanes lined up on final approach course 2, the left runway. Okay, so that's that. At this point, that's the last of the, because you really can't understand it until it's close traffic for real, and this is the most real. It's not the most real, but it's certainly one that allows you to feel like it's the most real position. So I kind of enjoy this particular simulation. So I think this is like $15 for this simulation, so it's really cheap, and I play it all the time. So anyway, so I think that's about it. Okay, I think ready for questions now, Michael.
Thank you so much, Stephen. Thank you for your presentation. Ladies and gentlemen, like Stephen just said, if you have any questions, this is your time. If you want to directly put forward any verbal questions for our speaker, Mr. Albania, you could go ahead. If you want to directly put forward any verbal questions, what you could do is you could click on the raise hand option, which is a palm-like icon on your participant screen. That way we can go ahead and unmute your individual lines and you can directly put forward your questions for Stephen, or you could send your questions using the chat column or the Q&A panel. So if you have any questions, ladies and gentlemen, please do go ahead. And also, while we wait for the question, just want to remind you all as well that if you do come up with questions or any suggestions any time after today's session, you could forward those over to us, and we'll make sure these are forwarded to our speaker to get you your answers. And also, today's webinar is available in a recorded format, so if you feel that any of your friends or colleagues or anybody else in your organization could benefit from today's session, you can have them log on to our website as well and make a purchase. But if you have any questions, ladies and gentlemen, for our speaker on today's topic, please do go ahead. This is your time. Stephen, I don't see any questions coming up. I'll just give it an extra 30 seconds to see if we do have any questions from our attendees.
Okay.
Ladies and gentlemen, I also would like to inform you all as well that if you log on to our website at complianceforall.com, we have a lot of topics which are available, which are coming up as webinars from our speaker, Mr. Stephen Albania, and you can make a purchase as well. We have one coming up in the month of July. It's Airport Traffic Control Tower and a few other topics. We have one at the end of July and one in August as well. So if you feel that these would be beneficial as well, you could log on to our website, or you could also give us a call as well, and we'll help you make a purchase. Stephen, I don't see any questions coming up from our attendees, so we'll go ahead and conclude the session. Before we do, any final thoughts, Stephen?
No, I don't. I think hopefully everybody enjoyed it and got something from it.
Wonderful. Thank you so much, Stephen. And ladies and gentlemen, I also would like to inform you all that the feedback form for today's session is open in the polling area, so kindly request you to go ahead and share your feedback on today's session. We have just over 8 questions, and they're all multiple choice in nature, so it shouldn't take you more than a couple of minutes before you log off to share your feedback. Again, we would appreciate your feedback. This would only help us in making our webinars better as we move along, and also gives an idea about today's session as well. So please do kindly share your feedback on today's session, and also for any questions or suggestions, please do forward those over, and we'll make sure these are forwarded to our speaker as well. And once again, ladies and gentlemen, I thank you all for participating in today's session, and on behalf of our speaker, Mr. Stephen Alvania, and the entire Compliance for All team, I'd like to thank you all, and hope the rest of the day is a lovely one. Thank you so much. And thank you so much, Stephen.
Thank you, Michael.